Hello, welcome to Lecture 15 in this series of Introduction to Proof talks. We're going to be covering a general introduction to the art of mathematics, section 3.2 today. This section is essentially a continuation of the previous one. In section 3.1, we covered the method of direct proof. And this is basically advice about what to do if you get stuck in a direct proof. So we're still talking about direct proofs, but we'll in particular talk about the forward-backward method, as some people call it, for deducing or for really finding the plan of a proof. The write-up is a separate issue. The example we're going to spend most of our time on is a thing called the arithmetic mean geometric mean inequality. People just say AM/GM. So first we're going to spend a little time hoping you to understand what AM and GM are, and then we'll actually prove the AM/GM inequality, and then we'll show a couple more examples of using this forward-backward idea to find yourself a proof. Okay, so the basic motivation for the forward-backward method is this advice people get, which is if you get stuck, you should try working from the conclusion back towards the beginning of the proof. So try working backwards. Now, that's not always the best advice because there's a directionality to a proof. So ideally, a proof has a shape like this. You'll have the hypothesis at first, or maybe at zeroth, the way I'm numbering them. There might be several of these. There can be a couple of statements that you use as hypotheses. There might be 0, 0.1, 0.2, however you want to number them. But then it looks like this. There's a sequence of deductions that you make. And we use the rules of inference that we previously learned to make these deductions. Deduction 3 has to follow from the hypotheses and deductions 1 and 2. And then there's a sort of an et cetera moment. And then eventually we get to the last statement, which is the conclusion. And if you see the way I'm counting, that's deduction n as well. All right, so yeah, remember this. Each deduction is just implied. Rules of inference are rules that tell you if the premises are true, then the conclusion will be true, but they do not go bidirectionally generally. So if you're stuck at some deduction along the way and you don't see any path forward towards the conclusion, maybe you can take the conclusion and back it up one. Figure out whatever deduction n-1 would be. Think about what statements imply your conclusion. Now, if the connection between your conclusion and deduction n-1 there is bidirectional, this is the same thing as making a deduction. This may not solve the problem, but at least you will have closed up the gap. You'll be closer to, you had before maybe 7 statements that you didn't know what they were. Now you only have 6, so you're getting better. Do recognize this. Sometimes deductions are connected with if and only if, especially if they're done just via algebra. Then or if they're one of the logical equivalences we formed before, those are if and only if statements. So those are awesome. If you've got an if and only if connector between 2 statements and you're working backwards, you can't mess that up. But sometimes the direction of the implications, it's truly unidirectional, in which case you have to kind of put yourself in a funny mindset where you intentionally think about converse errors, think about making a converse error. So what's the forward-backward idea? Back and forth. So sometimes you can reason from the conclusion all the way back to the hypothesis. And then, in fact, you work backwards through the whole thing. That's more or less the case with the proof we're going to do as an example first, the AM/GM inequality. But sometimes that doesn't work. So you may have to try working a little from the beginning towards, in the normal direction, and then a little from the end. And now you've reduced the gap to a smaller gap between statements. And now you just have to see if you can reason from that one to the other one. Again, looking backwards and forwards can be useful because, well, you'll have some idea of what your goal is, right? A better idea of what your goal is. And the hope, and it's amazing how often this will work out, you meet somewhere in the middle. Okay, so a few words on write-up, however. Everything we've just discussed is about the process of discovery, where you figure out, what's the argument, but you can't write it that way. Think of all that stuff as scratch work. You put that on scrap paper, and maybe you refer to it when you're doing a write-up, but in the end, like it says, a proof has to go from the hypotheses to the conclusion in that direction. It has to follow the directionality of the rules of inference. It has to go in the forward order. Sorry for yelling, but in the forward order. Do it from hypotheses to conclusion, not the reverse. So you got to make sure your write-up goes that way. Just throw away all the scrap work that you did originally to figure out what the proof would be, and then write it down from A to Z, not in reverse. Okay, so let's get moving on this example. We're going to do the arithmetic mean / geometric mean inequality is about arithmetic means and geometric means, AMs and GMs. So first we want to see what those are. Okay, maybe that's totally clear. AM stands for arithmetic mean, geometric mean is GM. I think everybody knows what the arithmetic mean is. That's really just the average. Add the two of them and divide by 2. So it's this. If the two numbers are x and y, the arithmetic mean is x plus y over 2. I should pronounce the parentheses better. It's the quantity x plus y divided by 2. So one way to approach this is to think about moving each of those operations up a level in the difficulty hierarchy. So I've often pointed out that the difficulty hierarchy is actually present on the calculator. Adding and subtracting are at one level. The next higher level is multiplying and dividing, because repeated adding is multiplying. Oops, putting the wrong place. Repeated adding is multiplying, and repeated subtracting is dividing. And then repeated multiplying is exponents. I guess you could think repeated division is like roots. But once you've got exponents, you can just think multiplying by a half corresponds to a power of a half when you go up. So what's that going to say for x plus y over 2? Adding becomes multiplying, so the x plus y will become an x times y. And the dividing by 2, that's the example I just did. It's really multiplying by 1/2. But multiplying turns into a power. So we're talking about x times y raised to the 1/2 power. Looks like that. Square root of xy. So that is a way to find a number that's somewhere in between two given real numbers. It's a kind of mean. The Greeks are the people who talked about this as the geometric mean. And let's look at y on a Desmos animation. Okay, so here I've taken kind of a lot of work to make an animation for you of what it looks like to have rectangles of all different aspect ratios, but which all have the same area. This is an animation of tall, skinny rectangles, and then wide, low rectangles, and in between there's things that are nearly squares, but they all have area 25. I just picked a random number, to be honest, when I did that. So let me pull up the animation. If I stop this at just the right point, we should have a square. Oh, let it go a little too far. Let me kick it back. Does that look like a square to you? Now, since all these families of rectangles had the same area, they all had area 25, and I'm going to just ask you to trust me. There's some funny business I played with Desmos to make that happen, but they did. They all have area 25. Think about, a low, wide rectangle, one that's like out here. It has maybe a height of y and a width of x. So x times y is this area. But when I bring it down to here, there it is, I've just got a 5 by 5 rectangle. The big width and the relatively small height of this square are sort of bookends for this side length of the square. One is smaller than the side length of the square, the other is bigger. You can see as I move the slider down towards the square region, the height is growing and the width is decreasing. So you've got two numbers that are bigger, and then they're just approaching a single number in between. Well, that's the geometry that they're talking about in the geometric mean. The area of any of these rectangles is width times height, so it's xy. If I call the x coordinate the width and the y coordinate the height. And to figure out the side length of the square, that's square rooting. So we're just taking the square root of the product xy. This geometric mean is literally defined that way in terms of geometry. It's the side length of a square which has the same area as a rectangle whose dimensions are x and y. I hope that clears up why you might call it geometric. Let's see if I've said the right things in the slides here. If you have an x by y rectangle, then it has the same area as an s by s square, right? Provided that s is the square root of xy. So, yeah, I sort of talked about this while we were looking at the animation. So you see that s is going to lie in between x and y. So that's sort of what a mean is for. A mean is some way of producing a number midway in between two given ones. It's just a question of what's your sense of midway mean. If you mean literally distance-wise, halfway in between the two, then sure, the arithmetic mean is what you want. But if you mean in terms of this geometry we've shown, then the geometric mean is the right thing. And there are other possibilities. There's something, for instance, called the harmonic mean. In fact, there's lots of different ways to find a number that lies in between two others. So there are many different means. This is probably your first exposure to multiple ideas of how to find an average, but there's, I don't know, at least dozens. and there's a lot of these inequalities that one can use as practice for doing proofs. Okay, so one thing we should notice, just this is a by the way moment here, the geometric mean would kind of blow up if one of x or y were negative. If you had a negative number under, well, one negative and one positive number under that radical, then you've got an imaginary result, and so you're no longer a real number. Yeah, so we'll come back to thinking about that. Now, I want to give you a different way to think about arithmetic and geometric means. You've probably heard these same terms, probably in Calculus 2, applied to sequences, an arithmetic sequence and a geometric sequence. Let me show an example on the calculator. I've already preloaded some sequences in here. So y1 has what's known as an arithmetic sequence. If you notice, it's growing, but it's growing slowly. It's not going crazy. Y2 has a geometric sequence. Oops. Go back to the 1 level. Or is there even a 0 level? There is. The geometric series in Y2, you can tell it's growing a good bit faster. And it starts out smaller than Y1, 3, and it's still smaller at this stage, but they're practically equal there. And then it takes the lead, and now it's more than twice as big, and it's growing rapidly. If you've probably seen exponential growth multiple times, that's a case of exponential growth there. Okay, so let's see about this in general. In an arithmetic sequence, there's a common difference between successive terms. If you just look at my terms 7 to 10, that's a difference of 3, 10 to 13, difference of 3, 13 to 16. They're all differences of 3. If you thought about creating a difference table like we did in the last lecture, it would just have two rows. You'd have the original sequence, and then you'd have a constant row, a row of all the same number, which was this common difference. So what about a geometric sequence? Well, that has a common ratio between the terms. Again, it has a little bit of this flavor of moving up one in the hierarchy of difficulty of operations. For y1, I was thinking about subtracting successive terms to get that common difference. Well, for y2, I'll think about forming the quotient of successive terms to get the common ratio. See that 6 over 3 is 2, and 12 over 6 is 2, and 24 over 12 is 2. You're doubling each time you move up this table. Okay. A little PS moment. There's actually a way to analyze a sequence if you think it has a geometric character by writing, instead of a difference table for it, writing a quotient table for it. And you could just as well have a quotient table that had multiple layers in it. This would be a quotient table that has just 2 rows. Formulas, maybe this is clear to you. An arithmetic sequence has the form a plus bx, and b would be that common difference. Going 1 forward in the sequence is like adding b to a term. A would be whatever your initial amount is. So in the y1 that I've got here, a would be 7 and b would be 3. Might as well just show it to you. See how it's 3 times x plus 7? Yeah. A geometric sequence has the form a times b raised to the x. Again, you see the pattern of turning adding into multiplying and turning multiplying into exponents. And y equals, see the way the pattern works here? This is 2 raised to the x power times 3. Well, I have to commute that to get what it shows on the slide, but 3 times 2 to the x. A is 3, b is 2. Yeah. Okay, I can leave that sitting there. These usages are related. In fact, they're the same notions as the ones we have for the means. So what does it have to do with the means in particular? These means actually provide a way to fill in a blank if you don't know what's there. That is, if there's a missing entry in a sequence, you use the appropriate mean and you can figure out what that missing entry is. This doesn't feel like rocket science when you do it for a arithmetic sequence. It seems obvious, but when it's geometric, it feels a little more interesting. And let me just point out that there's practical significance to this. The balance in an interest-bearing account is a sequence that goes up geometrically, because each compounding period you multiply by an interest rate. So you've got an exponent on the interest, well, 1 plus the interest rate. Anyway, they have a geometric character. So if you've got a missing bank statement, you can do the trick I'm about to show to figure out what the balance was in that missing month. So here's it's the same sequence we were just looking at. 7, 10, 13, something's missing, 19, 22, 25. Now, we were just looking at it, so we know the missing entry is 16. But notice that you can take 19 and 13, add them up, and you get 32, right? And then divide that by 2. 13 plus 19 over 2 doesn't give you the 16. So taking the average of the surrounding terms is what you use to fill in a blank. Here's the same idea applied with a geometric sequence. Well, it's the same one again. I guess I thought this out in advance. So we know that 24 is the missing entry, right? But that's just so you have confidence in that this actually works. The blank should be filled in with the geometric mean of the surrounding terms, the 12 and the 48. So we multiply those numbers and put them under a square root. And I just did this with a calculator. Square root of 576 turns out to be 24, which is what we thought. Okay, so that's a little thinking or helping you picture what the arithmetic mean and the geometric mean are and what they do. Let's get into this inequality that we're going to try to prove. First, I guess we ought to figure out what it is. The basic statement is the arithmetic mean is usually the bigger of the two. There is a case where they're equal to each other, and that's, well, what it says right there on the slide. If x and y are equal, then both of them will be equal to the common value. If y is equal to x, so you can replace a y with an x, you're averaging x plus x over 2, and you're geometrically square rooting the product of x times x. In both cases, you're going to come out with x. So the statement we want is something like this. The arithmetic mean is greater than or equal to the geometric mean. Because of the thing I've mentioned before about how the geometric mean can't deal with negatives under it, and there's another issue that's maybe more interesting. If you put both of the terms a and b, both negative, into this thing, you will get a positive number under the radical, right? So the square root of it will be defined and it'll be a positive number, but you'll have a negative number in this mean, in the arithmetic mean. And a negative number here is not going to be bigger than a positive number here. Right? So the statement's just not true when both numbers are negative. It's sort of impossible to say when one of them is negative and the other not. So we restrict to positive real numbers. We get, to put it formally, we restrict the universe of discourse. Here it is. Here's the formal statement. For all xy in R plus, x plus y over 2 is greater than or equal to square root of xy. Okay, so here's the problem. We've got hypotheses, and they're just that x and y are positive. That's all we've got to use. I don't see how we're going to go from x and y are positive to some inequality about the two different sorts of means. There is one step that you might be able to take, which is a fairly common thing people do, a no loss in generality piece of an argument. You say, look, if there's these two numbers, I could just say, I'm going to call x the bigger one or x the smaller one. It depends how you want to do it. But if I'm looking at two numbers and they weren't in the order that I wanted, I would just switch the names on the things until they were. So you can make this kind of an argument that one of them is the smaller of the two. You will sometimes see that abbreviated as WLOG. Most often when people are in a hurry working on a blackboard, they'll write WLOG. It means without loss of generality. If you want to be a little fancier, you can phrase this in multiple ways. So here's an option. You could say there is no loss in generality in assuming that x is greater than or equal to y. Maybe in parentheses, you could say, if it weren't, we would then just interchange the names of the variables or the quantities. But other than that, I don't see any possible move forward, and this doesn't help so much. Okay, I've got two positive numbers, and one of them's bigger than the other, and I'm supposed to get to this inequality about algebraic expressions. So a little voice in your head is, I tried to make it a little voice in your head. Try working backwards from the conclusion. So here's the conclusion. We want to conclude that x plus y over 2 is greater than or equal to the square root of xy. What would you do with that mess? I first, because I hate fractions, no, I don't hate them, but if you can clear fractions, it's going to make life easier. So I just multiply both sides by 2. Seems pretty reasonable. I also am not the biggest fan of square roots because, if we're working in integer arithmetic, square roots are going to take us out of that realm. Square roots have the potential to take us into the complex numbers. And they're algebraically complicated. So is it okay to square both sides? I think most people are cool with that. I should point out that actually that's wrong. That's generally speaking wrong to do. But we happen to be in a situation where it's okay to do. It's because we're dealing only with positive values for x and y. Okay, so what did I do next? I just FOIL rolled out the x plus y squared. Right? You see that's x squared plus 2xy from outer and inner terms, and then plus y squared from last times last. And then this last step is somewhat unmotivated, but people tend to do this. If you have something that looks quadratic, it's just a habit with polynomials to move everything to one side of the equation to get it to the form of a single polynomial equals or is greater than or equal, in this case, to some number, or even 0 if you can move the number part to the other side. Okay, so you're supposed to look at that and have a revelation. I don't know if you've had a revelation. If you're in the Cheyenne book, if you read that, it's got this note, whoa, we're done, when it gets to that. And I'm not sure if that was totally clear to people, that there was a reason for that level of excitement to say, whoa, we're done. So here's one more stage in it. Do you recognize? Oh, well, sorry. In JIM, they were using A and B, and in these slides, I've been using, let me go back, I've been using X and Y. So, yeah, JIM was looking at A squared minus 2AB plus B squared greater than or equal to 0. We were looking at the corresponding thing with X's and Y's. Anyway, that's just the expanded form of X minus Y squared. In this the thing I'm actually pointing at, it's A minus B squared. X minus Y squared greater than or equal to 0 would be related to the previous statement on the previous slide. Now, why am I excited about that? It's just that it's a square, right? Aren't squares always positive? In fact, not quite. If you have the square of 0, it'll be 0, but if it's the square of anything else, positive or negative, it'll be it'll be positive because, minus times minus is plus. So we're going to need to, in our actual proof where we go forward, we got to introduce this tautology that x minus y squared is always greater than or equal to 0. That's tautological over the real numbers. Yeah, that's a statement that's true for all real numbers, x and y. Probably we should prove it. I've kind of hand-waved at it. The problem is that it relies on a proof method that we're going to look at later. So when we get to the section on proof by cases, we'll look at this guy. It's a consequence of the thing called the trichotomy property. But again, let's put that off for a little while. For right now, don't you believe it that if you square a real number, you're going to get, at least 0 and possibly something much bigger than 0. So here's the proof, all chained together in the correct order, right? Suppose that x and y are particular but arbitrarily chosen real numbers. I really didn't need this one, but without loss of generality, we can say that x is the bigger of the two, so x minus y will be greater than or equal to 0. Then note that the square of x minus y is the square of a real number. That's all I need for this stuff. So I can deduce that x minus y squared is greater than or equal to 0. Maybe not deduce, I should claim it in this thing. If this is a great place if we were going to do the proof of that statement to introduce a lemma. So write a lemma that the highlighted thing is true, and then you can cite the lemma here and then move on to doing your algebra. So this is just the algebraic steps we discovered, but in the reverse order. We start out with the positivity, or rather the non-negativity of x minus y squared. Then we expand that out to get x squared minus 2xy plus y squared. I don't think many people would discover this step if they were trying to go in the forward direction. Even if you got that you needed to work with x minus y squared is greater than or equal to 0. But because of the direction we deduced it, this was obvious. Anyway, what has happened to go from the second row to the third row of this collection of equivalences? We've added 4xy to both sides. That's valid. If you have an inequality, you can add the same thing to both sides of it. What happened next is I noticed that this was the expanded form of x plus y squared, so I just did that algebra. And then I took a square root. Now, is that okay to do? We before said it was okay to square on both sides of an inequality. Is it okay to square root on both sides of an inequality? It turns out that's actually more valid, but I'll talk about that a little bit. And then finally, what are we doing? We're dividing both sides by 2 to get to arithmetic mean on the left, geometric mean on the right, and the greater than or equal sign in between. So QED, baby. Should we double check? Yeah, well, we always should double check. I'll get to that point that I mentioned that the deductions we came up with were going in the wrong direction. So unless they were if and only ifs, we could have had an error in here. And I'm particularly worried about, well, I just said that. What I'm particularly worried about is this step where we took the square root on both sides of an inequality. Is it really true that if I have two numbers, both of them positive, a and b, if a is the bigger of them, does that tell me that the square root of a is bigger than the square root of b? Well, probably shouldn't do it this way, but I'm cheating a little bit. I want to show you this by kind of a proof by picture. So I prepared a graph previously. Let's get that out of my way and I could click this. Thank you. This is the graph of the square root function. Right? And I've put out on the x-axis points for a and b. Right? So a is the bigger of them. And you notice that the square root of a is bigger than the square root of b. If you ask yourself, what was it about this graph that kept the square roots, or the function applied to a and b, in the same order as a and b were, it's that it's an increasing graph. Square root is an increasing graph everywhere. In fact, the square, y equals x squared, is the one that's got a problem with it. So the one that I think when I first said it, everybody, you don't have the chance to object because you're watching a static video, but I think it's probably got past most people that it's not okay to take the square on both sides of an inequality. For instance, if you had -3 is less than 3, and you square both sides, you get 9 is less than 9, but that's not true. Right? So Square root is actually the better one. If the two things are both defined, then the square root keeps them in the order that they were in. Okay, so that step is valid, and I think we're pretty comfortable with the other steps, so it's good. So, yeah, that's true. I'm sorry, I got behind on the slides. We just looked at the graph. Yeah, I think it's a good point in your careers to finally sort out this business with inequalities. When is it okay to apply some operation to both sides of an inequality? If you think about it as the application of a function, that is probably the best way to go. Generally speaking, we want the sense of the inequality to stay the same. And if you apply a function that is strictly increasing, or sometimes people say monotonically increasing, it never decreases, it always is going up. If you do that, then you are going to have the sense of the inequality remain the same on the version where you've applied the functions on both sides. If you have a strictly decreasing function and you apply that to both sides of an inequality, what it's going to do is reverse the sense of the inequality. And that's okay too, as long as it does something predictable, you're going to be fine with that. What you can't do is apply to both sides of the equation, or the inequality rather, a function that's not monotone. If it goes up and down, then some places it's going to mess up the order, and other places it won't. But depending on you've put in the potential for error, and that's just something you want to avoid. If you know that you've got a strictly increasing function, you can apply it to both sides. And this only needs to be strictly increasing on the universe of discourse you're dealing with. So when we were dealing with only positive numbers, it was okay to take the square. I'll point out this is a rule everybody knows. If you multiply an inequality by a negative quantity, you have to turn the inequality around. That's just one of those things you learn. Why is it true? It's because the function that's being applied is negate. It's f of x equals negative x, which has a graph that is decreasing with slope -1, right? So that's a case of the same idea. If you have a decreasing function, a strictly decreasing function, you apply it to both sides of an inequality, it'll switch the sense it'll turn the direction of the inequality around. Squaring in both sides of an inequality is, generally speaking, an invalid thing, but we were in the situation where it was r plus. So you're only looking at one half of the parabola, not the other half, which would cause you the troubles. So there, it's okay to do it. All right, so that's the proof of the arithmetic. I'm just going to say AMGM, the AMGM inequality, with a little bit more explanation about the steps of it. I think it's a good idea to see some more examples of this kind of thing. So here's a recreational problem. This is a great problem to bring up in like a math club and get people to work on it. What's the bigger fraction? 1999 over 2000 or 2000 over 2001? And sorry, no calculators. You have to do this, with your brain, not with calculators. Yeah. Okay, so let me point out that you can generalize this, and maybe it makes good sense to generalize it. This is just the x equals 2000 case of comparing these fractions with x's in them, x minus 1 over x versus x over x plus 1. If we can solve the question of which is bigger with the fraction with x's in them, then we can do the x equals 2000 would also be true. I honestly, looking at it at first, I didn't know the conclusion. Now I've actually been through it now, so I actually do know, but I'm claiming I don't know. Well, that's sort of meta. But that's okay. Look, you just work backwards from the conclusion, leaving a blank where the inequality symbol is going to go. Put that symbol of versus in there. I don't know whether it's less than or greater than. Actually, come to think of it, I'm not sure if I do know, because I've probably forgotten by now. But we'll see what it is supposed to be. You can just keep working backwards from the conclusion with this placeholder versus in there, and then later on you figure it out. Yeah, but we did do something that maybe isn't the smartest thing. Since we replaced the 2000 with x, there's possible values of x that mess up these two fractions. Think about, look at x minus 1 over x. If x is 0, you're hosed. You've got division by 0. And what value would make that go undefined? -1. So my take is, let's just go with positive numbers. We'll add the hypothesis that x is bigger than 0, and certainly 2000 is bigger than 0. So for the case we really care about, that'll be fine. Okay, so x is bigger than 0, and x plus 1 is bigger than 0. That's dumb, isn't it? If x is bigger than 0, certainly x plus 1 is bigger than 0. You added something to the big side. If you take an inequality and you make the big side even bigger, it's still going to be true. That's a process known as weakening the inequality. It doesn't have the teeth that it had, but it has exactly what we want. I want to know that x plus 1 is a positive number, because I would like to cross multiply to get those fractions into the form of just two products. Cross multiplying is just middle school algebra shorthand for the process of multiplying both sides by x and by x plus 1 in this case. Multiply by the denominators on both sides. All right, so we need to know that both of those are positive, or else we may mess up the direction of the inequality. But it's fine the way it is, because we've just put in an assumption that these guys would be positive. Yep, they're both positive, so good. So when we cross multiply, it looks like this: x minus 1 times x plus 1 versus x times x. Well, that's x squared minus 1 versus x squared. Which one's bigger? It's pretty obvious now. The versus should have been a less than sign, and so you go scratch out all the verses and put in less than signs, and you've got an argument that the x squared minus 1 must have been smaller than x squared. Now, I got to go back and see where we started with, though. The verses in right here should have been a less than sign. So we're pointing to the left. And that means this one, in the particular example we were after, was also pointing to the left. 1999 over 2000 is smaller than 2000 over 2001. And actually, you can see that directly if you want. Each of these numbers is just slightly less than 1, isn't it? How much less than 1? This is 1 over 2000 less than 1, and this is 1 over 2001 less than 1. Right? So this is a tiny bit less than the 1999 over 2000. That is, we subtracted a little more on the left than we did on the right, if you're thinking about taking that away from 1. Okay, so the other thing I wanted to look at is the product rule from calculus. Exercise 8 in section 3.2 asks you to use the forward-backward approach in proving the product rule for derivatives. And my experience with people using this book is that nobody sees the trick that you need to fill in. You go forward a little bit, you go back a little bit, but there's a point in the middle where you kind of get stuck. So it's too tricky of an argument, so I'm just going to lay it out for you. I tried desperately to make this happen in a technology way, but it just didn't want to. It's really hard to make a long argument like this unveil itself a little at a time. So I'm going old school here. This is a sheet of paper with the proof printed out on it, and I've got parts of it covered up because we don't want to see them yet. But the forward step is we start with the product. I need to point with something else so that my finger doesn't mess up the... No, that still messes up the focus. Well, maybe if I do it from out to the side. No, it still does. Anyway, the product of f times g's derivative is this expression. That's the limit definition of the derivative. And how do you work that? The function, which is the product of f and g, evaluated at x plus h minus the same function, the product of f and g, evaluated at x, divided by h. This is often called the difference quotient of this function. And you take the limit as h goes to 0. That's just the definition of the function. Oh, you know what? I just realized that I've skipped over a little discussion of hypotheses involved here. So let me point it out. Maybe it's a good idea to refresh your mind what the product rule looks like. For some people, it may have been years since they did calculus. The product rule says, it's also called the Leibniz rule, by the way. It's named after Gottfried Wilhelm von Leibniz. He is the guy who was kind of the co-inventor of calculus. Newton is sort of granted priority that he had invented calculus first, but he did something that I think is a little bit foolish. He decided that it was too cool of an idea to tell everybody about, and he could make himself look even smarter than he was, although he was regarded as the best mathematician in certainly England and perhaps all of Europe at the time. But he used his secret knowledge of calculus to prove various results that got him accolades but then he would go through laborious work to make sure that he recast it in a strictly geometric way so that it didn't give away the secret of taking derivatives and integrating and stuff. So Leibniz came along, 15 or quite a while later, and he said, "Hey, I've discovered calculus." And Newton said, "No, you haven't. I had it first," and pulled his stuff out of his drawer. But it caused a big argument. Anyway, if you take a history of math course, that's usually a thing that gets covered, the priority debate between Newton and Leibniz. And it actually caused, this is just math, but it actually caused bad blood. Like certain people took sides that one or the other of the gentlemen involved didn't care for. Anyway, there's a tendency when you're doing calculus that you skip over these fancy words that don't seem to have any real import anyway. You probably didn't notice that there's a hypothesis on the product rule, but there is, and it's this, that it's only valid if the two functions are both differentiable at x, or if you're thinking about applying this over an interval, you need to make sure they're differentiable across that entire interval. This is another one of these sort of theory-based things that people often kind of skip over, but if you've got a differentiable function at a point, that implies continuity at a point. And we will need both of those. We'll need that the functions are differentiable and that they're continuous at a point x. Yeah. Okay, so here's the low-tech version of this. I need to pop the window back on top. So first, I think I got through this already, that we've just written the definition of what it means to take the derivative of the function f times g. Right? And I know where I want to end up, by the way, right? I want to end up with this Leibniz rule, which looks like f prime times g plus f times g prime. Okay, so knowing that I want to end here, I can sort of back up one stage. I know that the ones that look like derivatives, f prime and the g prime, those should be replaced with the definition of derivative. Limit as h goes to 0. This was the one for g, and limit as h goes to 0, the difference quotient for f there. I put big parentheses around those expressions because one's multiplied by g of x, and the other's multiplied by f of x. All right, so let me show you all this junk in the middle. We are actually going to continue working. It looks hairy when you see it all at once, so I'm going to cover it up so we see just a little at a time. The first step I'm doing is the trick that people typically don't see. And if you just examine the difference between these two lines, you'll see that what happened is I took where it was previously just g of x, I wrote this expression. That's all I did. And that's a valid step. In fact, you can take that limit as the limit as h goes to 0 of g of x plus h. You can actually it feels like you can just plug in 0 for h, doesn't it? And you would just get g of x. That's where you're actually using the hypothesis that g of x is a continuous function. The limit there doesn't exist necessarily. Well, yeah, no, if g of x is not continuous, then that limit may not exist. In fact, if it's not continuous, it will not exist. But we know that it does exist because that function is continuous, because it is differentiable. That's part of the hypothesis for the product rule. Now, why did I choose to do that particular step? It's from looking at where we are and contrasting that with what we've got. Down below, we have things that involve f's and g's. Well, I should point at this one. You could distribute this g of x into the limit here because it doesn't have an h in it, right? You could get it inside the limit, and you'd have f times x plus h times g of x and minus f of x times g of x. Well, that's cool. I do want an f of x times a g of x. But I'm already going to get one of those from the other part. I get an f of x that I can distribute into this other limit, and I'd get minus f of x times g of x. What I'd really like to see up front is something that looks like f times g evaluated, both of them evaluated at x plus h. And that is the motivation for replacing g of x with g of x plus h. Now, that came at a cost. I've got it inside a limit. But we know because of continuity of g of x that that limit exists. We know because of differentiability of f that this limit exists. So remember your limit rules? Oh, I haven't done it yet. Oh, I've done a bad thing, actually. The parenthesis is in the wrong place. To take this limit and put it together with this limit is one of the rules for limits, that if you have the limit of a product, it's the product of the limits. I guess I'm using this one in reverse. So that paren needs to be right there. Sorry about that. Then it looks like on this line, two separate limits, but they're both being done with h going to 0, and they both exist, and so you can combine them into one limit, right? And then, well, next line, I think I'm distributing this f of x into the other guy. Now there I don't need the limit rule, because f of x, well, I guess there's sort of a basic rule that says if you have something that doesn't involve the variable under consideration, you can just move it in or out of the limit. So f of x is being distributed in. That's what we've got up on this line. The g of x plus h has been distributed into this one. The f of x has been distributed into that one. Now, again, we have two limits. And because of the way I designed this, with the one on the left having these x plus h signs, x plus h evaluation points, notice how you get the pieces we want. F of x plus h and g of x plus h there. I'm circling the wrong spot. I should have a circle right there, right? And then we've got the minus f of x times g of x on the end. And what do you notice about this junk in the middle? I hope you notice that they're the same thing, one of them with a minus sign and the other with a plus sign. So these guys just wipe each other out, meaning we get to that, meaning we get to that. So another example of mostly working backwards, but there was a little step where we worked forward from the first line to the second line. That was a forward deduction. And you could put this whole thing together into a unidirectional thing that went from premise to conclusion. The step here would feel a little weird at first because it seems unmotivated, but once you see how it works out, you go, oh, I see why they did that trick. And it is valid algebra to add and subtract the same thing from any part of an equation. So there you go. That's a more or less complete with one typo. Not bad in a piece of math that long. Proof of the product rule. And that's nice that we can prove the product rule, because once you have the product rule, you can put it together with the chain rule and you can prove the quotient rule. And then you've got sort of a massive arsenal of techniques you can apply in calculus. And I think that brings us to the end of today's slides. So thanks for paying attention. We will be covering section 3.3 on the next lecture, so some reading advance would be great. If you look through Giant 3.3, hopefully more of my mumbling will make sense to you. So have a great day. See you next time.